All right, so this week is going to be all about another application of how to use calculus and how to use the derivatives to do interesting stuff for us. And one of the most interesting things that we can use calculus for is to help us sketch the graphs of functions. And, I'm not talking about easy functions like x squared or x cubed or things like that. I'm talking about slightly more complicated functions. Like if I give you the natural log of sine of x, right? Can I figure out what that graph looks like and be able to sketch it by hand and be able to give you some really important information about it? And the reason why, this is going to be interesting to us is because in the real world, we model a whole bunch of things using functions. We might model things like, your profits. A business might try and model the cost. We might try and measure the acceleration of something, right? We have functions that model a whole bunch of things, and usually it's fairly interesting to us that if our function looks something like this and maybe has a spike, that we might want to know exactly when that maximum profit happens. Or if we have something like this and we get a dip, it's going to be useful to know when like the lowest cost is going to happen, right? Like what combination of materials and such do I need to purchase in order to get the lowest cost for my business? In terms of acceleration, right? Maybe you're designing a fighter jet and you're doing some testing, some stress testing, and you notice that the acceleration of the jet kind of does this, and you're going to need to know exactly when that peak acceleration happens because you need to know how much stress testing to put your pilots through because they need to be able to survive that amount of acceleration, right? The extra G's on their body. So one of like the primary uses of the first derivative here is actually to be able to figure out when like the maximums and minimums of functions exist. And what we're talking about here are two slightly different things. So I'll write them down. So when we're talking about maximums and minimums, there's a difference between what we call a local maximum / minimum and what we call the absolute maximum or minimum. And without doing any calculus first, I just like to draw you a picture of we'll say just a random little function here, right, that does this. Okay, and let's say this is my function f of x. To kind of get the idea of what a local maximum or minimum is, the idea here between this word local max or min means that if I think something is a local minimum, that means that if I were to like take a bubble, to create a bubble around this dot, right, that point would indeed have the smallest y value of every single other point in that neighborhood. Okay, so you might notice that, for instance, where I just drew that green dot is a local minimum, but this green dot wouldn't be a local minimum because no matter where I put a bubble around this dot, there's always going to be some smaller y values, right? There's going to be some lower points, which means that this green dot that I drew could not be a local minimum. Okay. Now, what makes it an absolute minimum? Well, an absolute minimum, the word absolute means we are considering every single other possibility, which means that our bubble is no longer going to be this small. It's not what we call local. We are looking at the whole picture. And if in the whole picture this ends up being the smallest y value, then this is what we would call an absolute minimum. And same thing, vice versa for the maxes, right? This right here would be a local maximum. That right here is a local maximum. Even here at the endpoints, now that's something interesting. That's also a local maximum because if we draw a bubble around this, right, all the other points on the graph are below it, right? They're all down here, which makes that a local maximum as well. But what you might notice is that if we do the absolute test, right, the absolute maximum test, this one is also the absolute max as well. So it is locally a maximum, right? Because if you just look at this little neighborhood, yeah, it's the head honcho. It's the highest one out of all of its nearby buddies, but it also happens to be the absolute maximum as well. Okay, so when we throw around the terminology local max, local min, absolute max, absolute minimum, that is what we are going to be talking about. Now I'm going to throw around another little bit of terminology as well, which is that, with graphs, it turns out that in order to sketch something, right, we already know how to do a lot of things with sketching, right? So maybe I'll write down things we already know how to do. Things we already know how to do, right? So for instance, we know how to come up with intercepts, right? That helps us graph things. What else do we know how to do? Maybe we know a bit about asymptotes, right? We have vertical asymptotes, and we also have horizontal asymptotes. Those things can help us, sketch a graph. But something else that can also help us sketch a graph, something we're going to add to this list over here on the left, is what we call like intervals of rising and falling. And what I mean here is that, if I have, maybe I'll put an axis here just to kind of give us some visual aid here. But the idea here is that, in between maximums and minimums, right, this is kind of easy to see here, our graph in this particular case on this particular little interval right here, maybe between here and here, our graph is going down, right? We would say that our graph is falling, or that our slope is negative in that particular region. Okay, and then maybe in the next little region, right, from here to this next maximum. Sorry for the conflicting colors. Maybe I'll switch to blue. Right, in this little interval between there and the next max, you'll notice that the graph it's on its way up, right? And so we would say, oh, the graph is rising there. Okay, and so that's what we mean when we talk about intervals of rising and falling. And this ability to kind of incorporate this information coupled with what we've already learned in pre-calculus allows us to sketch graphs and to kind of see what's going on. And one more thing that hopefully we learned in pre-calculus was this thing called end behavior. And end behavior, as a reminder, is like what's happening to this graph in the long run, right? As x gets bigger and bigger and bigger, or vice versa, as x kind of approaches negative infinity, right? It gets smaller and smaller. What is going to happen to this graph? These are all tools that we have at our disposal to sketch graphs. And so, we're going to basically just expand in this video on the tools we already have, and we're going to figure out how to use calculus to help us talk about these particular things right here. And it's actually not really too much too big of a thing for us to do. It's not going to be too hard. So let's talk about that. And actually, maybe let's grab this list really quick and kind of drag it down. I think that'll be useful. Okay, so let's put this here. Local max, local min, absolute max, absolute min, intervals of rise and fall. Things we don't yet know how to do, but we are going to learn how to do them. And again, I'll just put like a little random graph, and maybe I'll put some arrows at the end this time. Okay, a little random function here, f of x. So the first question that we're going to address is, how does f prime of x, give us information? Give us information about the graph. About the graph of f of x. Okay. And so the easiest way to think about this is to think about the simplest application of f prime, or of the derivative, which is that the derivative visually represents what? Well, the derivative visually is the slope of this particular graph. And so the idea here is that maybe if I know the slope of f of x at any given point, it should kind of make sense at the very least that I could figure out this last one, right? That I could figure out when my graph is going up, when my graph is going down, right? When is the slope positive? When is the slope negative? When is the slope positive? Et cetera, et cetera. So now the more interesting question is, what about these, right? Where would I find maximums and mims? What could you tell me about the slope, right? How does f prime come into play at all of these little local max and mins that I'm trying to find out? How does f prime come into play? What can you tell me is happening to the slope? Beforehand, we're going up, up, up. Afterwards, we're going down, down, down. Maybe down at a minimum, we're going down and then we're going up. What could you tell me is true about the slope at every single one of these points? And hopefully, you're saying to yourself, oh, well, the slope at every single one of these points is flat, right? The slope is 0, okay? Right at when a maximum or minimum occurs, the derivative is equal to 0. So I'm going to write that down. That's a big thing. So maxes and mins, and I'll say local maxes and mins. Local maxes and mins, actually, well, nah, forget it. Just maxes and mins, I'll just say can happen. Max and mins can happen when the slope is equal to 0, right? AKA when f prime of x is equal to 0. Now, what do I mean when I say can happen, right? You'll notice I'm not doing any math right yet, but when I say can happen, what could I be alluding to? Well, here's an example of a graph that you've probably seen, right? This right here, this graph is, this is y, oh, unless my pen doesn't want to work. Well, that graph that I just drew right there is y is equal to x cubed, and the graph of y is equal to x cubed, oh, my pen has decided to stop working. Oh, there we go. Okay, so the graph of y is equal to x cubed, right? You'll notice it does not have any maximums or minimums on it, right? It doesn't have any maximums or minimums, but right here in the middle, right smack dab there, the slope is flat, right? The slope is flat here. And so when I say max and mins can happen when the slope is equal to 0, we're going to need to look at a little bit more stuff. And it kind of makes sense, right? You'll notice that for a minimum to happen, the slope beforehand is going down, and then afterwards it's going up, right? And vice versa, for a maximum, right? For this guy up here, the slope has to be going up, and then it has to be going down. But what's going on right here, right? Because I have a slope of 0, right? Right at this point, I have a slope of 0, right? Or at least I claim that I do. But what can you tell me is true about the slope beforehand and afterwards? Well, the slope is going up, and then it's still going up afterwards. And so this would not give us a maximum. It would not give us a minimum. It just doesn't give us anything. We're just going to say that there is no maximum or min there, okay? And so what I'm going to write down is we're going to start now doing the math part. So we're going to maybe do a definition. And this definition is that what we call a critical point for f of x, for a graph f of x, is any point, or is any x value that gives us f prime of x is equal to 0, okay? A critical point is a potential candidate for being a maximum or minimum. So it's a potential candidate for being a max or min. For being a max or min, okay? And so now, right, now that we have that, okay, we basically figured out in the sketches that I did above that in order to determine if it's a max or a min, we're also going to need to know what's going on with the slope beforehand and afterwards. So I'm going to also add to this, in order to know in order to know if a critical point is a max or min, we'll need to look at the slope of f of x before and after the critical point. Right? And there's essentially three cases, okay? There's three cases with our critical points. There's case 1, case 2, case 3, which we already saw. If the slope is going down beforehand and then up afterwards, that means that our graph has to look something like this, and we're going to get what's called a minimum, okay? Now, if the slope is going up beforehand and down afterwards, well, then our graph is going to have to look something like this. And in that case, we're going to get what we call a maximum. And if the slope is doing both, in one direction, let's say it's going down and going down, that means that, we had to have been going here, we leveled out, and then we have to have resumed going down afterwards, in which case we get neither. Okay? Sometimes it's called a saddle. Sometimes it's called a saddle point, but we'll just call it neither for this class. Okay. Now you'll notice that I didn't specify, whether these are absolute minimums or max, right? They're all maxes and mins are inherently local max and mins, but I'm not writing if it's absolute or not because we would need at the end of the problem to look at all of the points and say, okay, which one's the biggest of the big and which one's the smallest of the small. But at this point, I think we have enough kind of intuition, a little bit of an idea of where we're aiming for. And so I think it's a good time to do an actual problem. So let's just do a problem. So for example, okay, so given, or actually I'll just say, let's just say what you'd see in the homework. Sketch y is equal to x cubed minus 3x squared plus 1 using, all of your calculus / math tools, right? You basically use everything that you know to come up with this sketch without relying on something like Desmos, okay? And so the first thing that I might do is I might, just run through my algebra stuff that I know. So the first thing I might look at is, okay, let's talk intercepts. Okay, intercepts. So there's two of those, right? There's a y-intercept. Now the y-intercept, if we're hitting a graph, remember if I have some sort of graph over here and my function is hitting that graph, it's hitting the y-axis, then what do we know about the value of one of the coordinates here? We're going to know that we don't know the y value, but we definitely know that the x value is going to be 0. And so in order to get the y-intercept, we set x equal to 0. So let x equal 0. And that's going to give us y is equal to 1. And so we immediately get that the point 0, 1 is our y-intercept right off the bat. So that's exciting. How about an x-intercept, right? Can we get an x-intercept? Now this one is what happens when we let y equal 0 because we're intersecting the x-axis. But this is going to lead us to the equation 0 is equal to x cubed minus 3x squared plus 1. And this particular cubic, at least, right off the rip, doesn't have a particularly nice answer or something that I can factor very easily. And so I'm just going to say, let's leave this be, right? We're going to leave b for now. Just because I can't solve it, okay? Now, how about asymptotes? Does this thing have any asymptotes? Does this have any place where it's going to blow up? Well, I don't see any square roots. I don't see any fractions with denominators that we have to be worried about. So we'll say that there's, at the very least, there's no vertical asymptote. Okay, and there's no vertical asymptote. So that's exciting. Now let's see. What's what's happening to this thing in the long run, right? What kind of end behavior does this have? Well, thankfully, we know that this is a cubic graph, and cubic graphs kind of look something like this, right? So it, we could basically make an educated guess that for end behavior, okay, now there's mathematical ways to do this, which we'll cover maybe a little bit later in the class when we talk about limits. But for end behavior, we'll say, as oops, I can type, as x approaches infinity, right? X gets bigger, what's happening to the y value of an x cubed graph? Well, y is also going to be approaching infinity. And as x gets more negative, right, the y value in this particular case is also going to get more negative. So this is all information that we have just from algebra class, from doing pre-calculus. We haven't even done any rigorous calculus yet. But now I guess is the time to kind of jump in there. So we'll zoom out a little bit and we'll try to do some calculus. Okay, so what does f prime give us? So the first thing that we're going to do is we're going to calculate f prime. Let's get f prime of x. So f prime of x in this case is 3x squared minus 6x. Okay. Now, some things that we talked about before. Number one, we know that, critical points happen. These potential candidates for maxes and mins, these happen when the slope is equal to 0. And so if we take that equation and we set it equal to 0, we'll get 0 is equal to 3x squared minus 6x. And then from here, we can factor the right side and get that x multiplied by 3x minus 6 is how this factors. And so this, we could pull out a 3 if we want, 3x times x minus 2. But this basically tells us that our critical points are going to be x is equal to 0 and when x is equal to 2. Okay, this is the only times when this graph has a slope of 0. Now, just keep in mind, this should kind of make sense because, again, this is a cubic graph, and a cubic graph kind of looks something like this. So we should expect to have one max, one min, something like this. So we expect to have two critical points. It should make some sort of sense. But now, kind of like what I said, is how do I know which of these is actually a maximum or min, right? If I keep this rough sketch, we could obviously tell just using some intuition that, okay, well, this one has to be when x is equal to 0, and this one has to be x is equal to 2, just using the preliminary knowledge that we know about cubic graphs. But for right now, we're going to pretend like we were working with some function and that we don't know this yet. And the question is, how would I figure this out? So the way that we typically figure out whether or not these are maxes or mins, remember, we need to know if the slope is going up, down, up, right? What's happening to the slope around and in between those critical points? And the best way to do this is to simply just create a number line, right? It's simply just to create a number line right here where we can put like infinity over here, negative infinity over here. And I'm going to put on here, I'm going to put x is equal to 0, and I'm going to put x is equal to 2. And why am I doing this number line? Because the goal is to figure out, what is f prime doing around our critical points, right? What's going on with f prime? And so what I mean is, all I need to do is to pick some x value that's here, right? I just need to test some x value over here. I need to test some x value that's between them, and I need to test some x value that's to the right. And if I just test those values and I you figure out what the slope is, then you're going to know what the slope is for this entire interval, right? You can kind of see it in the graph, right? If we know that the slope here, right, we already know what the answer is that we should expect is positive for literally every single value that's going from x equals 0 to the left, right? We know that. We can kind of see that's what we expect. But let's do it algebraically. So what I mean is pick your favorite x value that's to the left of this first critical point. Pick your favorite one. And here I'm just going to pick an easy one. I'm going to say, all right, let's try -1. Cool. Right there, there's f prime of x, right? All I want to know is the slope positive or is the slope negative? That is literally the only thing we want to know. So we're going to investigate f prime of -1. Okay, now there's two ways of doing this. The first way is probably the most natural, the thing that you would all try, which is you'd plug in -1, you do this squared -6 times -1, and you'd evaluate it, right? That makes sense. So we'd get like 3 minus a negative becomes a plus. We got +6. We say, oh, the answer is 9, which is a positive number. So that means that the slope on the left side of this point is equal to something positive. So we're going up. So sometimes I put a plus sign, or I kind of like to put an arrow kind of indicating that our slope is going up over there as well. But remember, all I need to know is I actually don't need to evaluate what this number is. All I need to know is whether or not it's a positive number or a negative number. And you might be saying, okay, right, that's what I did. Well, what I mean is you can shortcut this, right? You can look at 3x squared, right? If I plug in -1 like this, -6 times -1, you don't even have to do the math. You can just say, oh, that's going to be a positive number because I'm squaring something. So this first thing is positive. And then this second thing is going to end up becoming positive because I'm adding some number, right? Minus a negative. So I'm done. Positive. I don't even need to tell you that the answer is 9. You can just know that this thing is going to end up being some positive number. Okay? And this pattern kind of continues. We can do this strategy for everything that we're going to try. So, for instance, we just need to pick another point that's in between 0 and 2. So now let's try 1. All right, let's try some x value that's between these two critical points. And now let's test that into our derivative, into our slope. So f prime of 1. And now I'm going to do you one better. Instead of using that derivative that we came up with, which you totally could, I could plug in 1 and get that it's going to be a negative number, right? And in fact, I'll just do it really quick. 3 times 1 squared minus 6 times 1. This is equal to 3, and then I have -6. That's going to give me -3. That's a negative number. So I already know that this middle slope here is going to be negative, that the next bit of my graph is going down. Okay, we know that that's the case. But as a shortcut, people like shortcuts, we could actually just use this factored version of f prime. Remember, we took f prime, we took this thing and we factored it into 3x times x minus 2. Now, why would I want to use that, right? Why would I want to use that? And in fact, I'm just going to write it down here really quick. So we know that f prime of x factored into 3x times x minus 2. This is super useful because now if I want to figure out what f prime of 1 is, I can literally just look and be like, all right, what kind of number is this if I plug in 1? Okay, that's going to be a positive number. What kind of number is this if I plug in 1? Well, that's going to be a negative number. Last time I checked, what kind of number do you get when you multiply a positive and a negative? You're going to get a negative number, and that matches what we got here. It's a really slick trick to save you a lot of work in doing these calculations. So for the last one, right, I'll erase this. I'm going to rewrite everything down one more time. So, right, in the last one, let's pick another x value, and I'm just going to pick an easy one that's to the right of my last critical point. So x is equal to 3 here. And I'm going to write down what my derivative was again. It's 3x times x minus 2. And my goal now is to figure out what is f prime of 3. But again, I don't care exactly what it is. I just care if it's positive or negative. And when I plug in 3 into this, what am I going to get? I'm going to get a positive number. I don't care that it's 9. I just care that it's positive. And when I plug in 3 into this, what kind of number am I going to get? I'm also going to get a positive number, which means I'm going to have positive times positive, which is something positive. So this last little segment here is positive, and the graph goes up. And so from here, this immediately tells us information about these critical points, right? Remember, we had a critical point at x equals 0, a critical point at x is equal to 2. And so this immediately tells us that if we're going up beforehand and down afterwards, this has to be a local maximum. And this one has to be a local minimum. And above all, we actually just figured out what our intervals of rising and falling are. By creating this number line, we basically just figured out that our interval of rising, interval, right, all of the x values where our graph is going up is going to be all of the x's starting from negative infinity all the way up to x is equal to 0, right? Basically for this entire interval, the slope is positive. And then we jump over to this interval where the slope is back to being positive again. And so using interval notation, we'll put a union, and then we'll start at 2, and then we'll go all the way out to infinity again. Just as a quick commentary, you'll notice that I'm not using square brackets here, and that's just because at the end of the interval, you're not rising or falling, right? If you're at a maximum or a minimum, you're not going up or going down. So I don't include the endpoints there. I use open brackets to indicate that it's everything between and up to those critical points. And then for the last one here, if we're doing an interval of falling, right? Interval of falling, when is our graph kind of going down? We could say that that happens. Well, that interval is going to be the stuff in the middle here, courtesy of what we calculated before. And so that's going to be just what's going on between our two critical points from 0 to 2. Okay? And so this all manifests itself in the actual graph if we were to sketch it. And so what I'm going to do is I'm just going to kind of flip over to Desmos. Now, you would be expected to do this by hand, right? And I could, so maybe I'll roughly do it really quick. Using all of the information that we got, we have that there's an intercept, there's a y-intercept at 0, 1, so I expect my graph to hit there at some point. I know that x equals 0 gives me a local maximum, so that means not only is that thing going to be an intercept, but it's also going to be a max. So my graph has to kind of be doing something like this, right? And then let's see, x equals 2 is a local minimum. So how do I figure out what the y value is for that local minimum, right? If I know that x equals 2 results in a local min, what's the actual point? Well, I'm going to go all the way back up to the top and plug in 2 and figure out what it is. So I'm going to say, my function evaluated at 2 is going to be 2 cubed minus 3 times 2 squared plus 1. 2 cubed is equal to 8. This is 4 times 3 is 12. So I have 8 minus 12, which is a negative 4. Plus 1 is a negative 3. So this point on my graph is going to be somewhere down here at 2 comma negative 3. And I can continue with my sketch, right? I can say, okay, well, I'm going to get a minimum here. And then I know that my graph is going to go boop, 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 up like so, right? Using what we know about the end behaviors, this would be a reasonable sketch. And let's just check, right? Let's just check, and we'll use Desmos. And sure enough, right, here's our graph, right? Our graph for Desmos is basically saying everything that we just did, and it kind of matches, this sketch that we expected to get. So, okay, so this is one example, and understandably so. This is our very first example, and so maybe we'll do one more here. Let's do sine of x. Let's make some space here. Okay, so let's do as an example. So sketch y is equal to sine of x on the interval on the interval, let's do from x, it goes from pi over 2 to 2 pi. Let's make it kind of a funky interval, okay? And so we're going to use all of our, tools. Normally it would say find the maxes, find the mins, things like that. So maybe find all maxes and mins, intervals of rise and fall, right, etc. Okay, so basically everything that we just did. Let's sketch the graph of sine of x. Now I know that we know how to graph sine of x, that we've done it in our pre-calculus 2 class, but we're going to do it now using some calculus. So again, things that we could figure out, right? So is there going to be any intercepts? So is there a y-intercept when we let x equal 0? Okay, well, when x is equal to 0, we're going to get that y is equal to sine of 0. And yes, you do need to know how to evaluate your trig functions, but that's just equal to 0. And so we would get that an intercept for this thing is 0, 0. Now, we are only sketching on this interval of x values, and 0 is outside of this. So we actually won't really care about using this point. So that's one done. Now, how about the x-intercept? The x-intercept, that happens when y is equal to 0. And so if we set 0 is equal to sine of x, right, when does this happen? And we'd say, okay, well, using our trigonometry knowledge, we know that this is going to happen when x is equal to 0, when it equals pi, when it equals 2 pi, right, dot, 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 etc. And so on this interval, again, that we've been given over here, we're only really going to be interested about those two. And so that means that we are going to have the point pi comma 0 and pi comma 2 pi. 2 pi comma 0, excuse me. The x value is 2 pi comma 0, right? As our x-intercepts, the places when y is equal to 0. And just as a reminder, right, I'll roughly sketch what sine of x is supposed to look like in its entirety. Remember that sine of x looks something like this. So, and it keeps going forever and ever and ever in each direction. Just to have it there, kind of while we're doing this example. Okay, fantastic. So now let's examine critical points, right? We could do critical points, no problem. So critical points requires that we know what the derivative is. So f prime of x in this case, the derivative of sine of x is cosine of x. And if we're solving for critical points, we're specifically interested in when does cosine of x equal 0. Now, cosine of x equals 0 at different points. So this means, right, cosine is equal to 0 when x is equal to pi over 2 and 3 pi over 2. Now, it keeps going forever, but again, picking x values on this interval. So this means that our potential critical points are when x is equal to pi over 2, right, x is equal to pi over 2, and when x is equal to 3 pi over 2. And so now the question is, now we're going to test to see if they are maxes or mins. So we're going to take these, maybe go up here, and test if they're maxes or mins, okay? And so again, we're going to bust out a number line and say, look, I know that on this number line, I'm supposed to graph this function. Now, we are only interested in sketching on a particular interval. So I'm going to just kind of say that the end of this number line is going to be pi over 2 down here. The end of the number line over here is going to be 2 pi. And our critical points are as follows, right? So we already have one of the critical points, right there. And we have another critical point kind of over here at 3 pi over 2. Okay, at 3 pi over 2. And so we only really need to test, and again, in case you're wondering what's going on, we kind of expect that up here at pi over 2 and over here at 3 pi over 2 to have maxes and mins, right? We only need to test the values around those critical points. If we test the values around those critical points and see what's going on to the slope, we'll be able to determine whether or not we have maxes, mins, or whether we have neither. And again, I'm cheating because I already know what this graph is supposed to look like, but I'm just leaving it there. That way we kind of have something to guide us as we do this problem. Okay, so if I want to do some testing, I'm going to test a point here. I'm going to test a point here, right? I need to test points around my critical points. And so let's see, what's one that's right between pi over 2 and 3 pi over 2 that we could test? Well, last time I checked, between pi over 2 and 3 pi over 2 on the unit circle is pi, so that would be a good one to test. Now, 3 pi over 2 to 2 pi, this one probably a little bit more challenging to figure out, but again, depending on how fresh your knowledge of the unit circle is, remember our unit circle looks something like this, and 3 pi over 2 is at the bottom, and 2 pi is over here. So if we're picking a value that's going to be easy for us to calculate, maybe one in between, like 7 pi over 4 would be a good one. So let's test 7 pi over 4. And remember that our goal is to simply test to see what's going on with the slope around these critical points. So around this particular point here and this particular point here, we want to know what's going on with the slope. So we're going to bust out f prime, right? Remember that f prime of x was equal to cosine of x. And the question that we're going to ask is, what is the value of f prime at these points? So for instance, f prime of pi is equal to, well, what's cosine of pi? Cosine of pi is equal to -1, which means that my slope in this interval here is going to be negative, or that our graph, we expect it to be going down. And then the last one that we need to check would be f prime of 7 pi over 4, which is cosine of 7 pi over 4. And cosine of 7 pi over 4, so we can do this a couple ways. Remember, we don't actually need to know exactly what that value is. We just want to know if it's positive or negative. And the value of cosine, if we're in the fourth quadrant here, the value of cosine, which is the x value on the unit circle, the value of cosine over here is going to be positive. So this is going to be some positive. It ends up being positive root 2 over 2. But again, we don't really need to know that. We just care that it's a positive value. And so we're going to put that on our little interval right here. And now that I have all of that, we can put it together. We can start making a sketch. So let's do it. Maybe I'll scroll just a smidgen and start making a sketch. So we'll do this. We'll do this. Okay. And so I know that we're starting at pi over 2. We're ending this graph at 2 pi. Let's see. What else do we have? We have x-intercepts at pi and 0. So I know that it's probably a good idea to put pi and 3 pi over 2. Let's spread these out properly. Pi and 3 pi over 2 here. 3 pi over 2. Let's see. I know that at pi and at 3 pi over 2, I have intercepts. So we're hitting the graph. We're hitting somewhere there. And then let's see what else is going on. So, oh, no, those aren't intercepts. What am I saying? Those are the critical points. Our intercepts are at pi and 2 pi. Okay, so our intercepts are at pi. Let's try this again. Pi and 2 pi are the intercepts of our graph. And we have critical points at pi over 2 and 3 pi over 2. And we already figured out exactly what kind of critical points these are, because we figured out the interval of rise and fall. And so what we know, and we'll do it off to the side here, is that when x is equal to pi over 2, right? We don't know what the y value is, but I definitely know that this thing is going to be some point, and then I have like falling. That's what's going on, right? And then for the other one, I have 3 pi over 2 was my other critical point. Don't yet know what the y value is, but I know that this one is the result of the graph going down, then we hit the critical point, and then we go up. So at the very least, it looks like this is going to be a local max, and this one is going to be a local minimum. Now, how do I get those y values? Well, gosh, how do I get the y value of any function, right? How do I get the y value of any function? I'm just going to plug this value in, this x value, into my original function. So since we're trying to sketch y is equal to sine of x, we can just plug in pi over 2. And last time I checked, sine of pi over 2 is equal to 1. And then sine of 3 pi over 2 is equal to negative 1. And so that means that if I were to sketch those points, pi over 2 comma 1 would be up here. Pi over 2 comma 1. And then 3 pi over 2 comma negative 1 would be down here. 3 pi over 2 comma negative 1 is down here. And just using what we know, okay? Just use exactly what we know. We know that the graph is going down and up right here. We know that the graph is going down from this point. We're hitting these intercepts, and we just kind of, casually connect the dots. There we go. That's it. Just by using our intercepts and what we know about rising and falling and these critical points that we got, that's it. Here's our sketch. This is a good, educated, rough sketch based on all of the information that we had available to us and the tools at our disposal. And I think this is a good place to stop for this video. There's many more examples that could be done, but they'll probably be best served just kind of practicing them on your own in the homework. But what I will say is that there's even more tools that we have at our disposal to do a little bit more accurate curve sketching, which we'll get to in the next video involving the second derivative.